For generations, our vision of the dinosaur has been forged in shadow and fear. We imagine lumbering, monochrome monsters, their skin a uniform drab green or gray, their existence defined by a perpetual earth-shaking roar. This is the dinosaur of nightmare, a cinematic titan born from our fascination with the monstrous. But this image, as compelling as it is a relic of a bygone era of understanding. Science is now pulling back the curtain on this fiction, revealing a world far more complex, vibrant, and, in its own way, beautiful. The bones, once silent testaments to extinction, are beginning to speak. Through the lens of advanced imaging, biochemistry, and comparative anatomy, we are learning that the reality of these animals was not one of dull monstrosity, but of intricate design and spectacular appearance. The bones, once silent testaments to extinction, are beginning to speak. Through the lens of advanced imaging, biochemistry, and comparative anatomy, we are learning that the reality of these animals was not one of dull monstrosity, but of intricate design and spectacular appearance. The Mesozoic was not a gray world. It was a world painted in a full spectrum of color, texture, and form, a gallery of evolutionary artistry waiting to be rediscovered. This is a journey to look beyond the bone, to strip away the fiction, and to explore the surprising, evidence-based beauty of the dinosaurs. Our journey into this new vision begins with the very surface of the animal, its integument. For decades, we assumed dinosaurs were universally scaly, like their modern reptilian relatives. While many were, fossilized skin impressions have revealed a breathtaking diversity of textures that challenge this simple assumption. Consider the Carnotaurus, the meat-eating bull. Its exquisitely preserved skin shows not the overlapping scales of a snake, but a unique mosaic of small, bumpy scales interspersed with large conical studs, or osteoderms, running down its back and sides. This wasn't just armor, it was a rugged, patterned hide. Look to the heavily fortified Ankylosaurus, whose back was a landscape of fused bony plates and spikes, a masterpiece of natural defense that may have also served as a unique identifier for its species. These surfaces weren't just functional, they were statements. The intricate arrangement of scutes on a crocodile's back, the pebbled skin of an Edmontosaurus, each tells a story of evolution and adaptation, a form of beauty defined by texture, pattern, and resilience. Every fossil fragment peels back another layer of gray uniformity. Perhaps the most revolutionary shift in our perception of dinosaurs has been the discovery of feathers. Once thought to be the exclusive domain of birds, we now know that feathers, in some form, were widespread among many dinosaur lineages, particularly the theropods. These were not necessarily the complex flight feathers of a modern eagle. They began as simple, hair-like filaments, like the downy coat of the small carnivore Sinosauropteryx. Its fossil, unearthed in China, was so exquisitely preserved that it retained a halo of these proto-feathers, forever changing our image of its kind. The story gets even more vivid. Inside these fossilized feathers, paleontologists have discovered microscopic pigment sacs called melanosomes. By comparing their shape and arrangement to those in modern birds, we can reconstruct the actual colors of these ancient creatures. The Sinosauropteryx, we now believe, had a striking ringed tail of reddish-brown and white. This wasn't a monster from a B-movie, it was a real creature of subtle natural beauty, adorned with the very structures that would one day carry its descendants into the sky. The discovery of melanosomes opened the floodgates to a world of color. Dinosaurs weren't just earthy browns and greens. They were a symphony of hues, used for camouflage, warning signals, and, most dazzlingly, for display. The small four-winged dromaeosaur, Microraptor, provides a stunning example. Analysis of its melanosomes revealed that its feathers were not just black, but iridescent. Like a modern starling or magpie, its plumage would have shimmered with a glossy blue-green sheen in the sunlight. This wasn't just color, it was structural color, created by the microscopic architecture of the feather itself. This kind of ornamentation is rarely for hiding. It's for being seen. We see similar evidence elsewhere. The pot-bellied Pitacosaurus may have had countershading, a dark back and a light underside for camouflage, while the heavily armored nodosaur, Boreopelta, preserved in stunning detail, shows traces of reddish-brown pigmentation on its back, possibly for display. From the subtle to the spectacular, color was a fundamental language of the Mesozoic, a visual dialogue of attraction, deception, and identity played out on a global stage. Beyond skin and feathers, dinosaurs sculpted their own bodies into breathtaking forms of biological architecture. The elaborate crests, frills, and sails that adorned their skeletons were long dismissed as little more than weaponry. But modern science suggests a far more elegant and social purpose. The magnificent bony frill of a triceratops was too fragile and well-vascularized for brutal head-on combat. Instead, it was likely a biological billboard, a vast canvas for displaying patterns and colors to rivals and potential mates. The bizarre hollow crest of the Parasaurolophus was an even more sophisticated device. It wasn't a snorkel, as once thought, but a complex resonating chamber. By forcing air through its intricate nasal passages, this gentle giant could have produced deep, sonorous calls that echoed for miles across the Cretaceous plains, a form of auditory beauty. Even the dramatic sail of the Spinosaurus, long thought to be a simple heat exchanger, was likely a dynamic display structure, a towering marquee announcing its presence and vitality. These structures were the Mesozoic's crown jewels, transforming their owners into living works of art and communication. Nowhere is the concept of unconventional beauty more apparent than in the largest animals to ever walk the earth, the sauropods. It is easy to be overwhelmed by their sheer scale, to see them only as mountains of flesh. But to do so is to miss their profound elegance. An animal the size of a modern whale living on land is a paradox of biomechanical engineering. Their skeletons were marvels of lightweight construction, riddled with air sacs like a bird's, combining immense strength with minimal weight. Watch a herd of Argentinosaurus move in your mind's eye. See the synchronized, deliberate rhythm of their pillar-like legs, a slow-motion ballet of immense power. Witness the graceful, sweeping arc of a 50-foot neck as it reaches for the highest branches, its movement dictated by an efficiency honed over millions of years. Their bodies were living suspension bridges, with spines held in tension by enormous ligaments and muscles. Their every step was a testament to the elegant solutions evolution can produce when faced with the challenges of gravity and scale. Theirs is a beauty of form, function, and majestic motion. Beauty, in the end, is not just in the eye of the beholder. In the natural world, it is a language of survival. The startling patterns on a dinosaur's frill, the iridescent sheen of its feathers, the resonant call from a hollow crest, these were not random flourishes of nature's brush. They were vital tools for communication, for finding a mate, for establishing territory, and for distinguishing friend from foe. The beauty we are uncovering in the Mesozoic is the beauty of purpose. It's the elegance of a perfectly adapted predator, the vibrant warning of a well-defended herbivore, and the serene majesty of a herd moving as one. As our science becomes more sophisticated, our vision of the past becomes richer and more colorful. We are replacing the lumbering gray monsters of our imagination with vibrant, dynamic animals who were every bit as complex and visually stunning as the most spectacular creatures alive today. The bones still hold secrets, and with every new discovery, the lost world of the dinosaurs becomes not less mysterious, but infinitely more magnificent and beautiful. In the grand theater of the Mesozoic era, the most captivating performances were not always those of predation and survival. Beyond the terrifying teeth of the carnivores and the colossal bulk of the sauropods lies a more subtle yet equally spectacular story of evolution. It is a story told not through claws, but through crowns, not through armor, but through artistry. For millions of years, dinosaurs sculpted their own bodies, transforming their skulls into some of the most elaborate and baffling structures in the history of life. These cranial crowns and ornate crests are more than just fossilized curiosities. They are evolutionary masterpieces that challenge our understanding of what it meant to be a dinosaur. Why would a creature evolve a massive bony shield around its neck, or a hollow trombone-like tube atop its head? For decades, these questions have echoed through the halls of paleontology. The answers reveal a world far more complex and vibrant than previously imagined. A world of sophisticated communication and social signaling, where a dinosaur's head was its personal billboard, its musical instrument, and its standard in the great parade of life. Nowhere is this cranial extravagance more evident than with the ceratopsians, the horned dinosaurs of the late Cretaceous. The most famous of this lineage, Triceratops, was a formidable 9-ton herbivore whose identity is inseparable from its spectacular headgear. 3 immense horns, 2 above the eyes, 1 on the nose, jutted forward from a skull that could reach over 2 meters in length. But its most defining feature was the frill, a vast, solid shield of bone sweeping back from the skull to protect the neck. The obvious, long-held conclusion was that this was purely a defensive weapon, a shield and spear combination purpose-built to fend off the apex predator of its time, Tyrannosaurus rex. While it certainly could have served this function in a desperate moment, a closer look at the fossil evidence suggests a more nuanced story. The frill was not always solid bone. It was perforated by large openings and crisscrossed by deep grooves, which in life would have housed a rich network of blood vessels. This anatomy suggests the frill was not an inert shield, but a dynamic, living structure, perhaps covered in intricately patterned skin. This intricate vascular system points towards a primary function that had less to do with combat and everything to do with communication. The ability to pump blood through the frill would have allowed a Triceratops to flush it with vibrant colors, creating a stunning, unmissable visual display. This was its evolutionary billboard. In a world teeming with other large dinosaurs, having a unique and recognizable profile was crucial for identifying members of your own species. And the variety was staggering. Looking across the ceratopsian family tree, we see an explosion of cranial ornamentation. Styracosaurus boasted a frill bristling with enormous spikes. Centrosaurus featured a huge, curving nasal horn, while Cosmoceratops sported a bewildering array of hooks. Each species had its own unique coat of arms. Much like the antlers of modern deer, these structures were likely used in ritualistic displays to establish dominance and attract mates. The biggest, most vibrant frill belonged to the strongest individual. This was a silent language spoken in patterns of bone and color, a key to social status, recognition, and the continuation of the species. While the ceratopsians communicated through silent, visual spectacle, another group of dinosaurs filled the air with sound. These were the hadrosaurs, the so-called duck-billed dinosaurs, and among them, one stands out as a true maestro, Parasaurolophus. This gentle giant is renowned for the bizarre curving crest that extended up to 2 meters from the back of its skull. For years, scientists were perplexed by this structure. Was it a snorkel for breathing underwater, a weapon for combat, a foliage deflector? The truth, revealed through CT scans of pristine fossil skulls, is far more elegant and acoustically brilliant. The crest was not solid. Inside, it contained a complex series of hollow tubes that started at the nostrils, looped up and over the top of the skull, and then descended to the airway. It was, in essence, a perfectly designed resonating chamber. By exhaling through this intricate natural trombone, Parasaurolophus could produce powerful, low-frequency sounds. The old image of silent, primitive reptiles was being replaced by the sophisticated reality of a dinosaur designed to make music. The calls produced by this remarkable cranial instrument would have been unlike anything on Earth today. The long, looping tubes were ideal for generating deep, sonorous tones, perhaps akin to a foghorn or a French horn. These low-frequency sounds travel exceptionally well over long distances, cutting through dense forests and open plains with minimal distortion. This gave Parasaurolophus a powerful tool for long-range communication. A lone individual could signal its location to the rest of the herd. A scout could issue a deep, resonant alarm call at the first sign of a predator, alerting the entire group simultaneously. And during mating season, the air might have been filled with a Mesozoic symphony of competing calls. Fossil evidence shows variation in crest shape and size, linked to age and sex. Males may have had larger, more elaborate crests, capable of producing deeper, more impressive sounds than females or juveniles. This suggests a complex social structure and a rich vocal repertoire, painting a picture of a Cretaceous landscape that was anything but silent, regularly punctuated by the haunting calls of these hadrosaur virtuosos. The evolutionary drive for distinctive headgear produced yet another bizarre form in the Pachycephalosaurs, or thick-headed lizards. Pachycephalosaurus itself possessed one of the most curious skulls. Its head was crowned with an astonishingly thick, solid dome of bone, over 25 centimeters thick in large adults. This cranial dome was fringed with smaller bony knobs and spikes, giving it an ornate, regal appearance. The function of this natural battering ram is the subject of intense scientific debate. The popular theory envisions males engaging in headbutting contests for dominance, much like modern bighorn sheep. The dense bone and spine structure seems suited to absorbing massive impacts. However, some researchers argue the bone was better suited for flank butting, or that the dome was primarily a visual display, its size signaling maturity and strength. Whatever its precise use, the dome of Pachycephalosaurus is a testament to how far evolution could push cranial adaptation for social purposes. From the spiked shields of the ceratopsians to the resonating crests of the hadrosaurs and the domed skulls of the Pachycephalosaurs, a clear pattern emerges. These spectacular cranial structures were far more than simple curiosities. They were sophisticated, multifunctional adaptations that were central to the social lives of these animals. They served as species identifiers in crowded ecosystems, as instruments for complex communication across vast distances, and as visual advertisements of an individual's strength and fitness to potential mates and rivals. The Mesozoic majesty of these creatures was not defined solely by their immense size or predatory prowess, but also by this intricate, bony artistry. The skull, a structure typically associated with the basic functions of feeding and housing the brain, was transformed into a canvas for display and a chamber for sound. These cranial crowns and ornate crests provide us with an invaluable window into a lost world, revealing it to be more colorful, vibrant, and socially complex than we ever dared to imagine. For over a century, our image of the dinosaur was cast in stone and draped in scales. They were magnificent, formidable giants of a monochrome world, painted in speculative shades of green, gray, and brown. But this vision, as enduring as it was incomplete. Hidden within the fine-grained stone of ancient lakebeds, a revolution was waiting to be unearthed. A discovery that would not just change the details, but repaint our entire understanding of the Mesozoic era. The first hints were subtle, faint impressions around fossilized bones that defied easy explanation. Were they frayed tissues, decomposed skin, or were they something far more extraordinary? These delicate filaments were the prelude to a revelation that would connect the lost world of the dinosaurs to the vibrant avian life we know today. They were the fossilized whispers of feathers, proving that the divide between reptile and bird was not a line, but a beautifully feathered continuum. This discovery has launched a new chapter in paleontology, one that seeks to clothe these ancient skeletons not just in flesh and muscle, but in the spectacular plumage they truly possessed. The epicenter of this feathered revolution was Liaoning, a province in northeastern China. Here, in the early 1990s, farmers quarrying for shale uncovered a paleontological treasure trove. The fine volcanic ash that once settled in these ancient lakes preserved its victims with astonishing fidelity. Among them was a small theropod dinosaur named Sinosauropteryx. Etched into the stone surrounding its delicate skeleton was a halo of simple, hair-like structures. These were not the complex, veined feathers of a modern bird, but primitive filaments, or dino fuzz. This was undeniable proof. Sinosauropteryx was a non-avian dinosaur covered in an insulating coat. The discovery opened the floodgates. Soon, a spectacular menagerie of feathered dinosaurs emerged from the Liaoning deposits. Protarchaeopteryx, with symmetrical feathers on its arms. Caudiplectryx, with a fan of broad feathers on its tail, and many others, each a vital snapshot in the evolutionary journey of the feather. These fossils were not just bones, they were time capsules, preserving the soft tissues that forever changed our perception of what a dinosaur could be. The discovery of feathers raised a new question. What was their original purpose? The intricate architecture of a modern flight feather is an aerodynamic marvel, but the simple filaments of Sinosauropteryx or the symmetrical plumes of Caudipteryx were not capable of generating lift. The answer, it seems, is that feathers evolved for other reasons long before they were co-opted for flight. The most fundamental function was likely insulation. For small, active dinosaurs, a downy coat would have been crucial for maintaining body temperature, allowing them to thrive in a wider range of environments. But survival is only part of the story. The natural world is a theater of display. And feathers are a primary costume. The elaborate tail fan of Countipteryx, for example, served little purpose for insulation or flight. Instead, it was almost certainly a signaling device, used in courtship rituals to attract a mate, or in threat displays to intimidate rivals. This was a creature that strutted and showed off, its feathers a vital part of its social language, painting a picture of dinosaur behavior that is far more complex and bird-like than we ever imagined. For years, the color of these feathers remained a mystery, left to the speculation of paleoartists. Reconstructing the life appearance of an extinct animal seemed to be a permanent barrier of scientific inquiry. But a breakthrough came from an unexpected field, the study of microscopic structures within the feather itself. Inside the feathers of modern birds are tiny, pigment-bearing organelles called melanosomes. Crucially, the shape and arrangement of these melanosomes correspond to specific colors. Melanosomes, which are long and rod-shaped, produce black and gray hues. Phaeomelanosomes, which are small and spherical, produce reddish browns and yellows. In a monumental leap of scientific deduction, researchers discovered that these microscopic structures could be preserved in the fossil record. Using powerful scanning electron microscopes, paleontologists could peer into the fossilized feathers of dinosaurs and identify these ancient color capsules. The key to unlocking the true colors of the Mesozoic was there all along, locked away at a microscopic level, waiting for technology to catch up with our curiosity. With the melanosome key in hand, scientists could now do the impossible: restore color to a dinosaur with empirical evidence. One of the first and most complete canvases was a small four-winged dinosaur from China named Ankylosaurus huxley. The preservation of its feathers was so exceptional that paleontologists were able to map the melosome types across its entire body, from the tip of its snout to the end of its tail. The process was painstaking, involving the sampling of dozens of points on the fossil. The result was a revelation. Ankylosaurus was not a creature of dull earth tones. It was a strikingly patterned animal. Its body was predominantly covered in dark gray and black feathers. Its wings, on both its arms and legs, were adorned with bold white stripes, creating a dramatic spangled pattern. And as a final flourish, it sported a magnificent crest of russet red feathers atop its head. This wasn't guesswork. It was a portrait painted by microscopic data, a direct window into the visual world of the late Jurassic. For the first time, we saw a dinosaur in its true, vibrant colors. The discovery of pigment was only the beginning. Feathers possess another visual trick, one that relies not on chemistry, but on physics: iridescence. This shimmering, metallic sheen, seen today in hummingbirds and starlings, is a form of structural color. It's created not by pigment, but by the precise, layered arrangement of melanosomes, which scatter and reflect light waves in a specific way. Could dinosaur feathers have possessed this same dazzling quality? The evidence came from Microraptor, another four-winged gliding dinosaur from Liaoning. When its fossilized melanosomes were examined, scientists found they weren't just the rod-shaped melanosomes responsible for black pigment. They were unusually long, narrow, and arranged in flat, stacked layers, a microscopic architecture identical to that found in the iridescent feathers of modern birds. The conclusion was inescapable. Microraptor wasn't just black. It was glossy black, with an iridescent sheen that would have shimmered with hues of blue and green in the Cretaceous sunlight. It was a living jewel, gliding through the forest canopy, its appearance changing with every angle of the light. From simple fuzz to iridescent sheens, our understanding of the dinosaurian world has been fundamentally transformed. The scaly monsters of old have molted, revealing a dynasty of creatures far more complex, beautiful, and bird-like than we ever dared to imagine. This spectrum of feathers tells a story of evolution in action, of insulation, communication, and eventually the conquest of the skies. The science of color reconstruction is still young, and countless other species are waiting to have their true palettes revealed. Each new fossil, each microscopic examination adds another brushstroke to our ever-evolving masterpiece of the Mesozoic. We are no longer just reconstructing skeletons. We are reviving ancient ecosystems in their full, breathtaking color. The age of dinosaurs was not a drab and colorless era. It was a world buzzing with visual signals, adorned with vibrant crests, and illuminated by the shimmer of iridescent plumage. A true Mesozoic majesty finally seen in its proper light. In the grand theater of prehistoric life, no players commanded the stage with more presence than the sauropods. These were the long-necked titans, the largest animals ever to walk the earth, creatures of such impossible scale that they defy modern comparison. For over 140 million years, they were the dominant herbivores across every continent, their familiar silhouettes defining the Mesozoic skyline. But to see them merely as giants is to miss the true marvel of their existence. They were not clumsy, lumbering behemoths. They were masterpieces of biological engineering, living, breathing ecosystems in their own right. Their story is not just one of size, but of sublime adaptation and unexpected grace. We journey back to the Jurassic, to a world greener and warmer than our own, to walk in the shadow of these titans and uncover the secrets of how such majestic, moving landscapes were not only possible, but triumphant for an age. They were the true mountains of the Mesozoic, and their footsteps echoed with the quiet power of life pushed to its absolute physical limits. What anatomical alchemy allowed sauropods to achieve a size no land animal has rivaled since? The secret began deep within their bones. Unlike the solid, heavy skeletons of mammals, the vertebrae of a sauropod were intricate, hollow structures filled with air sacs connected to their respiratory system. This pneumatic system, similar to that of modern birds, dramatically lightened their skeleton without sacrificing strength. It was a framework of immense power, yet surprising delicacy. Their most defining feature, the colossal neck, was a triumph of this design. In some species, like Mamenchisaurus, it could be longer than a school bus, allowing them to graze vast areas without moving their immense bodies. This incredible reach was supported by a complex arrangement of ligaments and muscles, a living suspension bridge. At the center of it all, a heart of unprecedented power worked tirelessly, pumping hundreds of liters of blood up the towering column of the neck to a brain that, by comparison, was remarkably small. It was a body plan built for efficiency on a continental scale, a blueprint for gigantism. The life of a sauropod was an unceasing quest for fuel. To power a body that could weigh more than a dozen elephants, they had to consume immense quantities of plant matter every single day. Their feeding strategy was one of simple efficiency. They possessed peg-like or spoon-shaped teeth, not for chewing, but for raking and stripping foliage from branches. They would swallow mouthfuls of leaves, ferns, and cycads whole, letting their enormous digestive tracts do the hard work. This gut was essentially a massive fermentation vat, where symbiotic bacteria would break down the tough cellulose over several days, extracting every last drop of energy. We can imagine them moving slowly but purposefully through the lush Mesozoic forests, their long necks sweeping from side to side like colossal cranes. They were not selective eaters, they were bulk browsers, clearing vast swaths of vegetation. Their constant consumption not only fueled their own gigantic bodies, but also profoundly shaped the very landscapes they inhabited, acting as the primary gardeners of their age, pruning the ancient world. These gentle giants were not solitary wanderers. Fossil trackways, vast stretches of prehistoric mud now turned to stone, reveal a profound truth about their lives. They moved in herds. These fossilized footprints tell stories of entire communities on the move, a synchronized procession of titans. The logic is clear. In a world populated by formidable predators, there was safety in numbers. The herd was a mobile fortress. Larger, experienced adults would likely have formed a protective perimeter, with the smaller, more vulnerable juveniles kept safe within the center of the group. The ground would have trembled with their passage, a low-frequency rumble communicating their presence for miles around. This social structure was not merely defensive. It was a way of life, facilitating migration to new feeding grounds and potentially aiding in communal nesting. The herd was a superorganism, a single flowing river of life, composed of dozens of individuals, all connected by the shared, silent understanding of survival. Their collective presence was an unstoppable force of nature, a living geology shaping the land. Every titan begins life as something small and fragile. The journey of a sauropod from hatchling to colossus is one of the most extreme transformations in the history of life. Their lives began not with a live birth, but within a simple, spherical egg, often no larger than a grapefruit. Paleontologists have discovered vast nesting grounds, communal sites where females would bury dozens of eggs in the warm soil and leave them to incubate. Upon hatching, the infant sauropod was a mere miniature of its parents, perhaps only a few feet long and weighing less than a human baby. It was incredibly vulnerable. To survive, it had to grow, and grow at an astonishing rate. Evidence from bone histology suggests they could gain over 10 kilograms a day during their adolescent growth spurt. This meteoric rise was a race against time, a biological imperative to reach a size large enough to deter most predators. From a tiny creature hiding in the undergrowth to a walking tower of flesh and bone, their life cycle was an unparalleled epic of growth. Their immense size was their greatest shield, a passive defense that would have discouraged all but the most audacious predators. A healthy adult sauropod was a formidable challenge. Yet they were not entirely without specialized defenses. The Diplodocid family, including Diplodocus and Apatosaurus, possessed extraordinarily long, tapering tails. The final section was thin and whip-like, and it's hypothesized that a rapid flick could create a supersonic crack, a deafening warning shot to any approaching threat. Some Asian sauropods, like Sinosauropteryx, evolved a bony, spiked club at the end of their tail, a devastating weapon to be swung with precision. Others, like the early brachiosaurids, had large, sharp thumb claws that could have been used for stability or to inflict deep wounds. When confronted, a sauropod could also rely on its sheer mass, rearing up to bring its immense weight crashing down. While rarely needing to engage in direct combat, these giants were far from helpless. They were living citadels, well-equipped to defend their place in the Mesozoic ecosystem against formidable carnivores like Allosaurus. For an almost incomprehensible 140 million years, the sauropods were an unwavering presence on Earth. Their reign spanned the Jurassic and Cretaceous periods, a dynasty of giants that witnessed the rise and fall of countless other species. They were ecosystem engineers, their immense appetites and migratory patterns shaping the floral communities of the entire planet. Their passing through a forest would create clearings, allowing sunlight to reach the floor and encouraging new growth. Their droppings would redistribute nutrients over vast distances. But, like all dynasties, theirs eventually came to an end. The changing climate and flora of the late Cretaceous may have begun to challenge their specialized lifestyle even before the final cataclysmic asteroid impact. Yet their legacy is etched into the very rock of our world. They represent the absolute zenith of terrestrial life's potential for scale. To imagine them is to imagine a world of different rules, a world of silent, graceful giants moving like clouds across the ancient plains, a testament to the majestic and awe-inspiring artistry of evolution. In the grand, sprawling narrative of our planet, the Mesozoic Era stands as a testament to life's boundless creativity. It was an age not only of titanic scale, but of breathtaking artistry, where evolution, the master sculptor, worked on a canvas of continents. The driving force behind this creative explosion was a simple, primal imperative: survival. A constant, silent pressure exerted by some of the most efficient predators the world has ever known gave rise to an astonishing arms race. In the dense fern prairies and humid floodplains of the Jurassic and Cretaceous, to be large was not enough. To be a successful herbivore was to be a fortress. And in this crucible of predator and prey, defense was elevated to an art form. The skin, the skeleton, the very posture of these creatures began to transform. They became living sculptures, adorned with features as bizarre as they were brilliant, each one a masterstroke of defensive design, a biological solution to the ultimate problem of staying alive. Perhaps no creature better embodies this fusion of defense and display than the iconic Stegosaurus. Roaming the plains of late Jurassic North America, its silhouette is unmistakable, defined by the extraordinary structures rising from its spine. These were not simple scales or horns, but enormous kite-shaped plates of bone, or osteoderms, that ran in a staggered double row from its neck almost to its tail. For decades, their purpose was a subject of intense debate. While their sheer size offered some protection, their thin structure and rich blood supply suggest a more complex function. Paleontologists now believe these plates acted as sophisticated radiators, helping the colossal animal regulate its body temperature. But more than that, they were likely vibrant billboards. Flushed with blood, they could have blazed with spectacular color, used for species recognition or to intimidate rivals and predators. They were dynamic, living architecture, a breathtaking and perhaps beautiful solution to the challenges of a dangerous world. While the plates of the Stegosaurus may have been a passive, multi-purpose marvel, the animal's tail was an instrument of uncompromising, active defense. At its tip, it brandished 4 formidable dermal spikes, some reaching nearly a meter in length. This lethal apparatus is known rather whimsically as the thagomizer, a name coined in a 1982 cartoon that has since been adopted by paleontologists worldwide. But its function was no joke. This was a weapon of brutal efficiency. Fossil evidence provides stark confirmation of its use. An Allosaurus vertebra has been discovered bearing a puncture wound that perfectly matches the conical shape of a Stegosaurus spike, a wound that had healed but speaks to a violent encounter. The tail itself was not stiff, but highly flexible at the base, powered by immense muscles that allowed it to be whipped sideways with devastating speed and accuracy. This was not merely a deterrent, it was a precision weapon, a biological mace capable of inflicting crippling injuries, a stark reminder that this living sculpture was far from defenseless. As the Jurassic gave way to the Cretaceous period, the world changed. The predators grew larger, stronger, and perhaps even more cunning, with the rise of colossal carnivores like the tyrannosaurids. In response, the art of defense had to evolve, reaching its zenith in a group of herbivores that took the concept of armor to its absolute extreme, the Ankylosaurs. These were the walking tanks of the Mesozoic. Their name, meaning fused lizards, hints at their defensive strategy. Low-slung and powerfully built, their bodies were almost entirely encased in a formidable coat of bony armor. Unlike the Stegosaurus, which relied on a combination of display and an active weapon, the Ankylosaurs presented a more passive, impregnable fortress. Their primary defense was to hunker down, presenting a near impenetrable shield of bone and keratin to any attacker. They were the ultimate expression of a siege mentality, a lineage that traded agility for near invulnerability, becoming the quintessential living fortresses of their age. The masterpiece of this armored dynasty was arguably its most famous member, Ankylosaurus magniventris. Here, the concept of biological armor was perfected. Its entire upper surface, from its broad skull to the tip of its tail, was a mosaic of interlocking bony plates known as osteoderms. These were not just scales. They were plates of bone embedded directly into the skin, growing in a variety of shapes and sizes. Broad, flat scutes covered its back, while smaller, pebble-like ossicles filled in the gaps, creating a flexible yet incredibly tough hide. Even its eyelids were armored, with bony shutters that could slide down to protect its eyes. This was not a crude, heavy shell. It was a sophisticated, custom-fitted suit of armor, articulated and complex. Every element was a carefully shaped component in a larger defensive system, a testament to 100 million years of evolutionary refinement. The armor of Ankylosaurus represents a pinnacle of natural architecture, a sublime example of function dictating form in the most extreme and magnificent way. While its body armor was a masterwork of passive defense, Ankylosaurus was not without a powerful active response. Like Stegosaurus before it, its ultimate weapon was in its tail. But this was no thagomizer. Ankylosaurus had perfected a different kind of weapon, a colossal bony club. This incredible structure was formed from several large osteoderms fusing with the final tail vertebrae, creating a solid, heavy mass of bone. The tail itself was a unique piece of engineering. The posterior half was stiffened by overlapping vertebral processes and ossified tendons, forming a rigid handle-like structure. This allowed the entire tail, powered by massive muscles at its hip, to be swung like a sledgehammer. Biomechanical studies suggest the force of this impact would have been immense, more than capable of shattering the leg bones of an adult Tyrannosaurus rex. It was the definitive countermeasure to the bone-crushing jaws of the Cretaceous apex predators, a perfectly evolved hammer to meet the anvil of its time. The plates of Stegosaurus, the armor of Ankylosaurus, these were more than mere adaptations. They were the physical embodiment of a struggle for existence that lasted for millions of years. These creatures were living sculptures, shaped by the relentless chisel of natural selection. Their spikes, clubs, and shields were not just biological hardware. They were statements of resilience, testaments to nature's capacity for producing solutions that are elegant as they are effective. Today, their fossilized remains are the relics of a long-lost natural gallery. As we gaze upon their skeletons, we see more than ancient bones. We see the echoes of an evolutionary arms race, the majesty of survival, and the profound and often brutal beauty of life's unyielding drive to endure. They are monuments of the Mesozoic, reminding us that in the deep history of our world, survival itself was the greatest art form of all. In the theater of prehistoric life, the predator is often cast as the villain, a monstrous force of pure destruction. We imagine thunderous footsteps and earth-shaking roars, a narrative written in fear and finality. But this perception, colored by our modern sensibilities, misses a profound truth. The predator is not a monster, it is a masterpiece. Each serrated tooth, every perfectly articulated joint, each powerful muscle fiber is a word in a story of survival written over millions of years. This is not the art of malice, but the art of necessity. The shape of a claw, the curve of a jaw, the placement of an eye, these are not random acts of brutality. They are the elegant solutions to the most fundamental problem in nature, the acquisition of energy. In this chapter, we strip away the monster myth and look at the predator as an evolutionary artisan. We will explore the powerful grace and functional beauty of their lethal designs, seeing them not as engines of chaos, but as some of the most exquisitely adapted organisms ever to walk the earth. Theirs is a story of poise, power, and perfection. No creature embodies the predator myth more than Tyrannosaurus rex. Its very name means tyrant lizard king. For a century, we have envisioned it as little more than a walking jaw. But a closer look at its magnificent skull reveals a far more complex animal. This was not just a weapon, it was a sophisticated sensory hub. The enormous openings, or fenestrae, weren't just for muscle attachment. They drastically lightened the skull's weight without sacrificing strength, a marvel of biological engineering. Within this fortress of bone resided a brain with massively developed olfactory bulbs, granting it a sense of smell that may have been one of the most acute of any land animal ever. It could likely detect prey from miles away. Furthermore, its eyes were not positioned on the sides of its head like many other dinosaurs. They faced forward, providing excellent binocular vision and the crucial depth perception needed to track and pursue a target with precision. This was not a mindless brute. It was a calculating hunter that perceived its world in three-dimensional detail and with a richness of scent we can barely comprehend. The power of Tyrannosaurus was anchored in its chassis. Its body was a perfectly balanced engine of pursuit. The legs were immense pillars of muscle capable of generating tremendous force. Contrary to older tail-dragging depictions, we now understand its posture was dynamic and horizontal, far more like a bird's. The key to this incredible balance was its tail. Heavy, muscular, and held rigidly straight by a complex mesh of ligaments, it acted as a precise counterbalance to the enormous head and torso. Every step, every turn, every lunge was a coordinated movement between hips and tail, a biomechanical ballet of immense scale. And what of the famously small arms? For so long a subject of ridicule, even they speak to a story of specialization. With two-fingered hands and robust muscle attachments, they were far from useless. While their exact function remains debated,
perhaps for gripping struggling prey at close quarters or for helping the animal rise from a resting position. They represent an evolutionary trade-off, where energy and resources were diverted to what mattered most: the devastating power of the head and the locomotive force of the legs. Every part of the T-Rex was honed for its specific, lethal purpose.
Predatory perfection, however, is not solely a matter of size and brute force. On the forest floor and in the open plains, a different kind of hunter demonstrated a mastery of agility and precision. These were the dromaeosaurs, the running lizards, a family that includes famous names like Deinonychus and Velociraptor. Clad in a coat of sophisticated feathers, not for flight, but for insulation, display, and maneuvering, they were among the most bird-like of all dinosaurs. Their design prioritized speed and reflexes. A lightweight, hollow-boned skeleton provided the frame for a high-performance metabolism. Their true innovation, however, was the weapon that gave them their terrible claw reputation. The sickle-like claw on the second toe of each foot was held retracted while running, kept sharp for its singular purpose. Fossil evidence and biomechanical studies suggest this claw wasn't for slashing or disemboweling as popularly imagined. Instead, it was likely used as a grappling hook, a tool to pin down smaller prey while the dinosaur maintained its balance with its feathered arms and long, rigid tail, allowing the jaws to do the final work. This was predation as a calculated, precise art form. Not all of the great predators stalked the land. The vast river systems of the Cretaceous period were a world unto themselves, and they were ruled by a different kind of giant. This was the domain of Spinosaurus, perhaps the largest carnivorous dinosaur that ever lived. Its anatomy was a striking departure from its terrestrial cousins, a clear testament to a life spent in and around water. The skull was long and narrow, almost crocodile-like, and filled with conical, unserrated teeth, not for slicing flesh, but for gripping large, slippery fish. Recent discoveries have revolutionized our understanding of its body plan, revealing a creature even more specialized for an aquatic environment than we ever imagined. Its hind legs were relatively short, and its feet were broad and possibly webbed, better for paddling than for running. Most astonishingly, its tail was not the thin, pointed tail of a typical theropod, but a deep, paddle-like structure, a powerful fin to propel its immense body through the water. The famous sail, a series of neural spines rising from its back, remains a subject of debate, but it would have been a spectacular sight rising from the murky Cretaceous rivers, a warning, a display, and the unmistakable signature of the master of the waterways. The hunt is the predator's defining moment, the ultimate expression of its specialized design. Yet, to view it merely as an act of violence is to miss the intricate strategy involved. A hunt is a calculation of risk versus reward, a profound expenditure of precious energy that cannot be wasted. A large carnivore like Tyrannosaurus would not charge recklessly into a healthy herd. Instead, it would observe, using its keen senses to assess the group, to identify the telltale signs of weakness. It would look for an individual that was young, old, sick, or isolated, a target that offered the highest probability of success for the lowest energy cost. The approach would be one of stealth and patience, using cover and terrain to close the distance. The final attack would be a sudden, explosive burst of power, a controlled application of force designed to end the encounter as quickly as possible. Every step, from the initial observation to the final decisive action, is a demonstration of evolutionary strategy.
It is a chess match where the stakes are life and death, and every move is dictated by the unforgiving laws of energy economics. The raw power is but the final act in a play of intelligence and efficiency. The reign of the great dinosaurs ended in a global catastrophe, but the legacy of the predator's poise endures. These creatures were not nature's villains, they were its sculptors. Through the constant pressure they exerted, they drove the evolution of their prey, forcing adaptations for speed, for defense, for heightened senses. They were a critical, balancing force in their ecosystems, ensuring the health of herbivore populations and the stability of the entire food web. The beauty we see in their fossils is more than just bone deep. It is the beauty of function, of a problem solved with lethal elegance. Every skeleton we unearth is a blueprint for a perfect hunter, a testament to natural selection's power as an artist. As our science advances, we peel back the layers of monster mythology and replace them with a deeper appreciation. We see not a monster, but a marvel. We see the powerful grace in the arch of a neck, the calculated design in the curve of a claw, and the undeniable majesty in the predator's timeless evolutionary poise. Their art was the art of survival, and its gallery is the fossil record itself, waiting for us to understand. For all that we unearth, the deep past remains a place of profound silence. The bones, trackways, and fossilized impressions we recover are mere echoes of a vibrant, living world. They are fragments of an epic story, a biological puzzle with most of its pieces lost to the relentless grind of geological time. How, then, do we bridge this immense chasm between skeletal remains and the breathing, dynamic creatures they once were? The answer lies at a remarkable intersection of scientific inquiry and artistic vision, the discipline of paleoart. This is not mere fantasy or illustration. It is a rigorous process of visual hypothesis, a crucial tool that translates complex data into a language we can all understand. Early attempts, like the lumbering sculptures of Victorian England, were noble but flawed reflections of their time. Today, paleoart stands on a foundation of evidence, transforming our perception from that of sluggish, scaly monsters into the sophisticated, magnificent animals that modern science has revealed. It is the first step in breathing life back into the silent stones. Every reconstruction begins with the skeleton. It is the blueprint, the non-negotiable framework that dictates the animal's fundamental architecture. Working in close collaboration, paleontologists and artists meticulously assemble this bony scaffold, guided by the fossil evidence. The posture, the proportions, the range of motion, all are locked within the shape and articulation of the vertebrae, limbs, and skull. But bone is only the beginning. To truly resurrect a creature, one must understand its musculature. This is the science of myology. How can we know where powerful muscles attach to long extinct bones? The fossils themselves provide the clues. Faint ridges, rough patches, and distinct crests on the bone surface are known as muscle scars, or rugosities. These are the anchor points where tendons and ligaments once held firm. By mapping these scars and comparing them to the anatomy of modern relatives, like birds and crocodiles, artists can painstakingly reconstruct the muscle groups, layer by layer. The skeletal frame of a triceratops transforms from a static mount into a powerful chassis, capable of supporting its immense weight and anchoring the muscles that powered its formidable charge. With the underlying form established, the artist must now create the animal's vital envelope, its skin. For decades, this was largely a matter of educated guesswork, often defaulting to a generic reptilian scaliness. But extraordinary fossil discoveries have pulled back the curtain, revealing the true face of the dinosaurs in breathtaking detail. We have found skin impressions from hadrosaurs like Edmontosaurus, so exquisitely preserved they are called mummies, showing a mosaic of varied, non-overlapping scales. We have found the strange bony studs or osteoderms that dotted the hide of the predator Carnotaurus, giving it a uniquely pebbled appearance. And, perhaps most revolutionary of all, we have found feathers. Not just on small bird-like dinosaurs, but on colossal tyrannosauroids like Utyrannus. These were not the sleek feathers of flight, but a shaggy, insulating coat of primitive filaments. Such direct, tangible evidence has fundamentally reshaped our vision, replacing monochrome monsters with creatures of intricate texture and surprising delicacy. The giants of the past were not just scaly, they were studded, pebbled, and profoundly feathered.
For every child and every scientist, one question has always loomed large. What color were the dinosaurs? For over a century, the answer was, we can't know, leaving their coloration to the speculative whims of the artist. But that has changed forever. In a stunning convergence of paleontology and molecular biology, scientists have discovered a way to see the echoes of color in the fossil record. The key is microscopic structures called melanosomes. These tiny organelles, which contain pigments, can be preserved for over 100 million years. By studying their shape, size, and arrangement within fossilized feathers and skin, and comparing them to the melanosomes of modern animals, we can decode the original colors and patterns. This technique first revealed the striped reddish-brown tail of the small theropod Sinosauropteryx. It then unveiled the remarkable camouflage of the armored nodosaur Boreopelta, which sported a form of countershading, dark on top, light on its underside, to help it hide from predators. Paleo art is no longer painting in the dark. It is working with a palette recovered from the deep past itself. Where the fossil record falls silence, science and art turn to the living world for inspiration. This is the principle of plausible inference, using modern biological analogs to inform our reconstructions. No direct evidence tells us precisely how a theropod stood or ran, but the powerful digitigrade legs of an ostrich or an emu provide a compelling model for their dynamic, athletic posture. We have no fossilized sound from a Parasaurolophus, but the intricate, hollow structure of its crest bears a striking resemblance to a brass instrument. By studying modern animals that use resonating chambers for communication, like certain birds, we can infer that this dinosaur likely produced deep, haunting calls that echoed across the Cretaceous plains. The extravagant casques of cassowaries used for display and navigating dense forests offer a plausible explanation for the function of similar structures on oviraptorosaurs. This is not baseless speculation. It is a careful, comparative process that uses the known functions of today's biology to fill the gaps in yesterday's, ensuring that every artistic choice is rooted in what is possible and probable in the natural world. A dinosaur, however perfectly rendered, is incomplete without its world. The final, crucial layer of paleoart is the reconstruction of the ecosystem. This elevates a simple portrait into a living narrative. Creating these environments is a science in itself, a grand synthesis of multiple disciplines. Paleobotanists provide the cast of floral characters, from the towering Jurassic conifers and ginkgos to the newly evolving flowering plants of the Cretaceous. Geologists map the ancient landscapes, defining the shape of coastlines, the course of rivers, and the rise of mountain ranges.
Even trace fossils, the footprints and trackways left behind, inform the artist, revealing details about herd behavior, predator-prey interactions, and the type of substrate the animals walked upon. A truly masterful piece of paleoart is a complete immersion. It places a herd of mighty Argentinosaurus not in a void, but within a vast fern prairie, their immense feet stirring up dust under a hazy sky. It shows a pteranodon soaring not just through the air, but over the specific waters of the western interior seaway, its shadow falling upon the ammonites swimming below. It creates a window into a lost but complete world.
Ultimately, every piece of paleoart is more than just a beautiful image. It is a scientific statement. It is a visual hypothesis, a snapshot of our collective knowledge at a single point in time. And like any good hypothesis, it is subject to change. The art evolves as the science evolves. The slow, tail-dragging swamp dwellers of a century ago gave way to the more active, land-based creatures of the dinosaur renaissance. Those, in turn, have been refined into the dynamic, feathered, and intricately colored animals we envision today. Each new fossil, each new analytical technique provides the artist with a fresh set of data, a new detail to incorporate. Paleoart is therefore a living, breathing field, an ongoing, dynamic conversation between the silent evidence of the rock and the human desire to understand and to see. It is the final, vital translation that allows us to look back across an unimaginable gulf of time, not just to analyze bones, but to witness for a fleeting moment the breathtaking Mesozoic majesty of a world brought back to life.